Put a pencil in a glass of water, and it looks broken. The water isn't bending the pencil, it's bending the light. Master this one idea, and all of ray optics falls into place. Here's another one. Place a coin at the bottom of an empty bowl. Pour in water, and the coin appears to rise up toward you. Same trick, bending light. Now look again. In both tricks, nothing about the object changed. The pencil never bent. The coin never moved. Only the light changed direction. And that one idea, light bending at a boundary, is the whole chapter. Light travels slower in water and glass than in air. When it crosses the boundary at an angle, one side slows before the other, so the beam pivots. That bending is called refraction. Let's label it. The ray coming in is the incident ray. The line straight out of the surface is the normal. The bent ray is the refracted ray. The angles are always measured from the normal, never from the surface. How much a material slows light is captured by one number, the refractive index n. It's simply the speed of light in vacuum divided by its speed in the material. Bigger n means slower light and stronger bending. But where do those sign terms actually come from? Picture the light as a marching wavefront. When it meets the boundary at an angle, one edge reaches the slower medium first and falls behind. So the whole wavefront swings around, and the ray bends toward the normal. That geometry is exactly what gives us Snell's law. n1 sine theta 1 equals n2 sine theta 2. This is why a swimming pool always looks shallower than it really is, and why a fish appears closer to the surface than where it actually swims. So, why does it look shallower? Light from the object bends as it leaves the water, and your eye simply traces those bent rays straight back. They meet at a point higher up, the apparent depth. And dividing the real depth by the apparent depth gives you exactly n. Now flip it. Send light from water back out into air. This time it bends away from the normal. Increase the angle, and the refracted ray leans closer and closer to the surface. At one special angle, the refracted ray runs exactly along the surface at 90 degrees. That incidence angle is called the critical angle. Go even steeper, past the critical angle, and there's nowhere for the light to escape. All of it reflects back inside. This is total internal reflection. The critical angle drops right out of Snell's law. Put the angle of incidence as c and the refracted angle as 90 degrees. Since sine of 90 is 1, sine of c equals 1 over n. Total internal reflection is everywhere. It pipes light down optical fibers across oceans. It makes a diamond sparkle, and it paints that shimmering water mirage on a hot road. Real lenses are built from curved surfaces. So let's refract light at a single spherical surface. An object sits in a medium of index n1. Light refracts into n2 and forms an image. The surface has radius r. Watch how little it takes. For rays close to the axis, these angles are tiny. So the tangent of each angle is just the angle itself. The exterior angle rule gives I equals alpha plus gamma and r equals gamma minus beta. Put those into Snell's law for small angles. n1i equals n2r. Substitute the distances, and the whole thing collapses into one clean relation. Here it is. n2 over v minus n1 over u equals n2 minus n1 all over r. This one formula describes refraction at any spherical surface. One warning that trips up everyone in exams: the sign convention. Measure all distances from the pole, take the incoming light as traveling left to right, and distances against that direction are negative. Get the signs right and the numbers just work. Now the payoff. A thin lens is nothing but two spherical surfaces back to back, with radii r1 and r2. So we just apply our surface formula twice. At the first surface, light from the object forms an intermediate image. That image becomes the object for the second surface, which forms the final image. Two applications of the same equation. Add those two equations. The intermediate image cancels out. And for a lens in air, you get the lens maker's formula. 1 over f equals n minus 1 times 1 over r1 minus 1 over r2. Once you know the focal length, the lens itself obeys the simplest rule of all. 1 over v minus 1 over u equals 1 over f. This single line solves almost every lens problem you'll meet. And to find how big the image is, magnification equals image height over object height, which also equals v over u. Positive or negative tells you upright or inverted. One more formula, and examiners love it. The power of a lens is just 1 over its focal length in meters, measured in dioptres. A shorter focal length bends light more strongly, so more power. Converging lenses have positive power, diverging lenses, negative. Let's use it. A converging lens has a focal length of 20 centimeters. We place an object 30 centimeters in front of it. Where does the image form? Plug into the lens formula. 1 over v equals 1 over f plus 1 over u. Work it through and v comes out to 60 centimeters. A real, inverted image on the far side. Step back and look at the chain you just built. Refraction, Snell's law, total internal reflection, the spherical surface, the lens maker's formula, the lens equation, and power. Every one flowing from a single idea. Light bends when it changes speed. Before you go, 5 quick questions to see if this chapter really stuck. Question 1. Reverse the viewpoint. A fish looks almost straight up at a bird flying 3 meters above the water. Refractive index of water, 4/3. Where does the bird appear to the fish? A. 2.25 meters. B. 3 meters. C. 4 meters. Or D. Right at the surface. 5 seconds, pause if you need more time. Did you pick A, 2.25? That's the classic move. Divide by n, just like the coin in the bowl. But that rule is for looking down, into water. The fish is looking up, out of it. Reverse the viewpoint, and the factor reverses too. So the right answer is C, multiply. 3 times 4/3, the bird appears 4 meters up, higher than it really is. Question 2. Light travels from air into water, hitting the surface at 60 degrees. 60 is bigger than the critical angle, 48.6. So, total internal reflection? A, yes, the angle beats the critical angle. B, no, it can never happen this way. C, partially. Or D, only in deep water. 5 seconds on the clock. If you said A, yes, it's trapped, you remembered half the rule. Bigger than the critical angle, so it must reflect, right? But total internal reflection has a second condition. The light must be going from denser to rarer. Here it's going from air into water, the wrong direction entirely. So the answer is B. The ray just bends toward the normal and walks straight in. 60 degrees outside becomes about 41 inside. No reflection, no drama. Question 3. An object sits just 10 centimeters in front of a converging lens of focal length 20. Where's the image? A, real, 6.7 centimeters behind. B, real, 20 centimeters behind. C, virtual, 20 centimeters in front, upright and doubled. Or D, no image at all. Think signs. 5 seconds, pause if you need more time. Did you get A, 6.7? Then you added 1 over 20 plus 1 over 10, and forgot the sign. Distances to the left are negative, so U is minus 10. Run it again. 1 over V equals 1 over 20 minus 1 over 10, that's minus 1 over 20. So the answer is C. V is minus 20, virtual, same side, upright, and twice as big. You've just built a magnifying glass. Here is question 4. Take a glass lens, refractive index 1.5, and dip it into water. What happens to its power? A. It stays the same. Power is power. B. It drops to about 1/4. C. It increases. Or D. It vanishes completely. 5 seconds. Pause if you need more time. If you chose A, that feels safe. Surely power belongs to the lens. But the lens maker's formula says power lives in the contrast between the lens and its surroundings. In air, n-1 is 0.5. In water, the relative index is 1.5 over 1.33. barely 0.13, so the answer is B. The power collapses to about a quarter. And if the water matched the glass exactly, the lens would simply disappear. Last question, and this one is sitting on someone's nose right now. An optician writes -2.0 dioptres. What lens is that? A. Convex, focal length, plus 50 centimeters. B. Concave, -50 centimeters. C. Concave, -2 meters. D. Convex, plus 2 meters. 5 seconds. Pause if you need more time. Threw away the minus sign or picked C? Here's the catch. Power is 1 over F, with F measured in meters. 1 over -2 is -0.5 meters. That's -50 centimeters, not 2. And the minus sign means concave, a diverging lens. So the answer is B. But hold on. Why would anyone put a lens that spreads light out in front of their eye? That's the best part. Because your eye is this entire chapter in miniature. The cornea and the lens together make a converging system of about 60 dioptres, stronger than any spectacle ever prescribed. A healthy eye lands a perfect sharp point exactly on the retina. In nearsightedness, myopia, the eyeball is a fraction too long. The sharp point forms just in front of the retina, and distant objects smear into a blur. The fix? Spread the light slightly before it enters, a concave lens. That is exactly what -2 dioptres means, a -50 centimeter diverging lens that walks the focus back onto the retina. Farsightedness is the mirror image. The point forms behind the retina, so close-up text blurs. The fix is a convex lens, positive power, the +2 dioptre reading glasses from earlier. So next time you see spectacles, read the number. That little letter D is this whole chapter, sitting right on someone's nose. And that is worth a smile. That's the whole heart of ray optics. No memorizing, just understanding. If this made lenses finally click, subscribe, and tell me which chapter to animate next.